Going to be working on the homework solutions for 3-5 inverse trig functions. And the first 6 problems don't have anything really to do with calculus. These are just pre-cal problems, and in pre-cal you studied inverse functions, inverse trig functions. So just this is kind of a reminder of how these things work. So for part A it says to find arc sine of root 3 over 2. So what we want to do is remember that this is asking us where on the unit circle, at what angle, is the y-coordinate root 3 over 2. And the reason why we're saying y-coordinate is because this is arc sine. So this is really saying like sine of what angle, right? This is the question, what's theta, will give us root 3 over 2. And remember, on the circle, the x-coordinate is cosine of the angle, and the y-coordinate is sine of the angle. So if we recall where our common values on our unit circle are, the y value being root 3 over 2, that's going to happen here. That's at the point 1/2 root 3 over 2. And then it also happens over here at negative 1/2 root 3 over 2. So these both have the same y-coordinate. This is 60 degrees, or pi over 3. And this one is 2 pi over 3, or 120 degrees. However, because this is an arc sine, or an inverse sine function, when we define this in pre-cal, we said that we had to do some restrictions on the domain of sine in order to define the inverse function. So what that means is that our answer here has to live between, I have to cut off the second and third quadrants. Our answer must live between pi over 2, which is up here, and negative pi over 2. So again, you might have to go back and review your pre-cal stuff. Just remember that our restriction here makes it so that one of these answers is not going to be possible. The only answer is this one, because it's the only one that lives within that domain restriction. So the answer here would be pi over 3. Now for number 2, or part B, I should say, we're being asked to find where arc cosine is negative 1. So where's arc cosine negative 1? That means, again, we're going to look at our unit circle, and this time we're looking at the x-coordinate because it's arc cosine, and we want to know basically cosine of what angle is equal to negative 1. So at what angle do we get an x-coordinate of negative 1? Well, here's the point negative 1, 0. That's the only point on the unit circle where we have a negative 1 for our x-coordinate. That angle here is pi. Now we could also say like negative pi to get there. However, our domain restriction to be able to define the arc cosine, we had to cut off the bottom part of the circle and only look between 0 and pi. So that means the answer here would be pi, not negative pi, and nothing bigger than pi. All right, let's look at number 2. Arc tangent of 1 over root 3. Arc tangent of 1 over root 3. All right, so this is again asking us tangent of what angle is equal to 1 over root 3. And if we go to our unit circle, our domain restriction, the domain restriction that is required to be able to define the inverse tangent, is we had to look only again between negative pi over 2 to pi over 2. So we can only look here in the first and fourth quadrants. Now tangent, remember sine and cosine corresponded to, sine was the y-coordinate, cosine was the x-coordinate. on this unit circle. Tangent, because tangent is sine theta over cosine theta, and this has got to be equal to 1 over root 3, we need to know where the ratio, on the unit circle, where's the ratio of the y-coordinate over the x-coordinate equal to 1 over root 3. So it's positive, right? This is a positive number. And since in the first quadrant, both your x and y coordinates are positive, I know that I must be up here. I can't be down here because in this quadrant, we have a positive x coordinate and a negative y coordinate, so the ratio would be negative. So I know I'm not down here. Now the only common points here that I know are, this one is root 3 over 2, 1/2. This one is 1/2 root 3 over 2. And this one right here is root 2 over 2, root 2 over 2. So I want to take the sine of the angle divided by cosine of the angle. That's y coordinate over x coordinate, and I want it to be this. Let's just throw out this one, because if I take the y coordinate and divide it by the x coordinate, that's 1. Can't be that one. How about this one? If I take the y coordinate, root 3 over 2, and divide it by the x coordinate, 1/2, then I can flip, right, multiply by the reciprocal, and the 2's would cancel, and you just get root 3. But that's not what I want. I want 1 over root 3. So it's got to be this last one here. Let's check it, though. If I take the y coordinate, 1/2, divide it by the x coordinate, root 3 over 2, and then do my flipping, multiplying by the reciprocal, then the 2's cancel, and I get 1 over root 3. And that's exactly what I wanted. So I know that this point corresponds to the tangent of the angle being 1 over root 3. So to find the inverse tangent, what I need to know is what was that angle, and that's pi over 6. All right, next one, part B, secant inverse of 2. Or arcsecant of 2. All right, well, arcsecant is, this is, oh, hold on just a second. Oh, let me take this real quick. All right, sorry about that. Okay, so what this is saying here, again, is secant of what angle is equal to 2. And let's remember that secant is 1 over cosine. When is that equal to 2? And if I multiply both sides by cosine theta, I get 1 is equal to 2 cosine theta, and then divide both sides by 2. This is saying, where's cosine theta? 1/2. So again, I go back to my unit circle. cosine is the x-coordinate. Where's the x-coordinate 1/2? Well, that happens here, and it also happens here. But remember, we have to throw out, there's a domain restriction, and the domain restriction that we have for to be able to define the secant inverse is the same as the one we have for cosine. So we throw out the bottom 2 quadrants, and that means this is the only angle that would give us that. By the way, this is the point 1/2 root 3 over 2. X-coordinate is 1/2. Cosine theta, that's the x-coordinate, is 1/2. And so that angle right there is pi over 3. 60 degrees. All right. I think you can do, I hope you can do 3 and 4 on your own. Let me take a look at 5 and 6. So how about 5? We've got tangent of arctangent of 10. Now, this one's going to be a little bit trickier. Your natural instinct here is to say, hey, look, a function, you compose it, right? This is tangent of, so you're doing composition. You're composing a function with its inverse. They should just kill each other off, and this answer should be just 10, which is the thing that was getting plugged in, which I agree with, but you have to be careful with this. First, we need to know, what is this saying? This is saying that we want to find an angle where tangent of that angle is equal to 10. And we come here to the unit circle. Because we're looking at tangent and we're looking at its inverse, we cut off these 2 quadrants. Tangent being positive means we must be in the first quadrant. And we need tangent, which is the ratio of the y-coordinate over the x-coordinate, because it's sine over cosine. We need that to be 10. So somewhere on here, we are going to get 10. I don't know where, but it's some angle. I don't know what that angle is. I'll just call it theta. I don't know what it is. The reason I know that I can get 10 is if I actually look at the graph of tangent. The graph of tangent goes like this. Here's pi over 2. This is where we have a vertical asymptote. And remember, we're only looking between 0 and pi over 2 anyway, so I'm not even looking over here. And since this goes to infinity, as you get closer to pi over 2, I know somewhere in here, right, at some angle theta, I'm going to be 10 units high eventually. So this is well defined. I'm going to get some angle here, theta. All right? I'm going to get some angle there, theta. And then when I take tangent of that angle, it's going to spit back where it came from. So go back here. When I said arctangent of 10, that meant, hey, give me this angle right here. So it's theta. But then I said, hey, now take tangent of that angle. So take tangent of that angle, and you go right back up to 10. So this is correct. Now, this may, again, may seem obvious, but let's look at B. B is the one that's tricky. We're going to do arcsine of sine of 7 pi over 3. Now, if you use that same logic that we just used, and you just right off the bat say, oh, these are going to kill each other off, the answer is just going to be 7 pi over 3, you're going to see it's not going to be correct. And here's why. First, let's figure out what is sine of 7 pi over 3. Well, all right, so where is 7 pi over 3? You'd have to count your way around the circle, but this is 1 pi over 3, or pi over 3. This is 2 pi over 3, 3 pi over 3, 4 pi over 3, 5 pi over 3, 6 pi over 3, and then 7 pi over 3 would take you back here, all right? So you just count your way around that 7 pi over 3. If I say what is sine of 7 pi over 3, that means I want the y-coordinate, and this is that point 1/2 root 3 over 2. So this right here is root 3 over 2. So now we're saying to ourselves, what's arcsine of root 3 over 2? What we need to do is remember that because we're talking about arc sine, our answers must be stuck between negative pi over 2 and pi over 2. We cannot go all the way around and back to this angle, or to this point, by passing through that region. So if this is saying where is your y coordinate, root 3 over 2, we are going to say, oh, it's this angle right here, and that angle right there is actually pi over 3. So this is equal to pi over 3. So that means this answer is pi over 3, not 7 pi over 3. All right, this is pre-cal, and I'm not trying to teach it to you here. I'm just trying to get you to remember these things from pre-cal. So I will let you mess with the rest. I'll let you mess with 6. 6 is a little messy, especially part B. I'm curious to see what you do on that. I'll give you a hint. You can use a double angle formula for 6b. All right, 16. Now we get to some derivatives, which is really the main point of this section. Let's say we're given y is equal to arctangent of the quantity x squared. And we want to know the derivative. Well, let's first remember that the derivative, if y is equal to tangent x, the derivative of that is 1 over 1 plus x squared. That's the formula for this section. For, arctangent, not tangent. Derivative of arctangent of x is 1 over 1 plus x squared. So when we come over here, we're going to have to realize that we have chain rule. We have arctangent of something. So the derivative of this should be 1 over 1 plus whatever was in here, right? Whatever was in there, squared. So it's going to be x squared squared. But because it's chain rule, I now have done the arctangent. I need to look in here and attach to this with multiplication the derivative of this, which is just 2x. So if we just clean it up, we get 2x on top, and on the bottom we have 1 plus x to the 4th power. There we go. X squared squared is x to the 4th. Now, number 17, slightly different problem. Is arctangent, the whole thing, arctangent x, that quantity squared. So instead of squaring just the x, we're squaring the whole thing. Again, this is chain rule. We have something being squared, we're taking the derivative. So that means the 2 will drop out. We'll have arctangent of x, all of this to the 1st power, which I didn't need to write, but I'm just showing you that was power rule. Now that we've done the square, we move inside and we take the derivative of what was in here. The derivative of arctangent of x, well, we just talked about that. That's 1 over 1 plus whatever's here squared. And that's it. So I can rewrite this as 2 arctangent x over 1 plus x squared. All right, 18. G of x. Ooh, did I turn my microphone? Okay, good. G of x equals root x squared minus 1 times secant inverse of x. All right, so we have a product rule here. There's your product right through there. And so I'm going to apply the product rule when I take the derivative. The derivative of this should be the derivative of this one, which we've done derivatives of roots a lot now. So this should be 1 over 2 times the root of whatever was there. Chain rule says now go inside the root, because you've already done the root. Take derivative of what's in here, that's 2x. So I put a 2x here. And notice that if I put the 2x here, the 2's would cancel and I could slide the x on top, which I will do. Like that. Times the second one, so I'm doing my product rule now, plus, now the derivative of the second one, these formulas are on page 183, is 1 over x squared, or sorry, x times the square root of x squared minus 1. So that is your derivative of arcsecant, just right off the formula. And then I have times this one, which is square root of x squared minus 1. And notice that this and this cancel, so this is just 1 over x. So your answer will be this plus 1 over x. And we'll just leave it like that. All right, next one, number 19. Arc sine of 2x plus 1. Y equals? Y equals. There we go. All right, so we have chain rule again because we have arc sine of something. The derivative of arc sine, again, that formula is on page 183, is going to be 1 over the square root of 1 minus whatever's here squared. Okay, that's the derivative of arc sine of something. It's 1 over the square root of 1 minus that something squared. But the chain rule says you've done derivative of that, take derivative of the inside, which is just 2. So I can just pop that 2 on top and I'm done. All right, number 20. Arctangent of x minus, oh my goodness, y equals arctangent of x minus square root of 1 plus x squared. All right, that doesn't look good. All right, let's not panic. We're taking the derivative, it's chain rule because we have arctangent of something. The derivative of arctangent of something is 1 over 1 plus that something, which is this big ugly thing, squared, times chain rule, go inside, take derivative of what's in there. I have 2 terms, so I'm going to give myself some room and I'm going to use parentheses. Derivative of x is 1, minus the derivative of the root of something. I have a chain rule right here, is 1 over 2 times the root of that something, times derivative of what's inside, which is 2x. So there's your derivative of x. This is the derivative of this right here. The 2's cancel. The x goes on top. And I'm guessing this is not what the back of the book's going to have. They're probably going to clean this up. Let me see. 1 plus x minus square root 1 plus x squared times 1 minus x over root 1 plus x squared. Well, maybe they will leave it like that. I doubt it. I doubt it. Let me see what I can do to this to try and clean it up. Let me get a common denominator between these 2 terms. So I'm going to turn this 1 into an x over x, like that. Right? And if I do that, whoa, what happens? No, let's not do that. I mean, I can write that, but what I was trying to get it to look like is this over here, but I don't think that's going to work. Okay. Try not to expand that out. All right, so let's do a common denominator here. So I'm going to put over here, instead of 1, I'm going to put root 1 plus x squared and then root 1 plus x squared. I feel like I'm going to get myself into trouble here. All right, so we have, this is equal to 1 over 1 plus x minus root 1 plus x squared squared, okay? And then over here, if I have the same denominator, I can put these together, it's gonna be this minus this. So root 1 plus x squared minus x over the common denominator, which is root 1 plus x squared. Man, do I want to multiply that through? I'm going to check to see what if they simplify. I know I can keep going with this, but if they left it like that, I'm just going to leave it also. So what I can see here is I can maybe like expand this out and then put everything together. I got the raw derivative, at least that part of it's done. Okay. This is chapter 3, 3.5. This is number 20. Whoa, I went too far. Whoa. Jeez. Sorry about making you wait here. I'm really hoping they don't go any further. Oh, they do. Okay, yeah, they multiplied out. All right, so I'm going to expand this. I'm going to multiply that times itself. So I'm doing this times itself. And when I do that, I get 1 over 1 plus, all right, this times this is x squared. In the middle, I get x times that big root, right, negative. Then on the inside, another one of those, so I'm going to get negative 2x times that root. And then when I do the outside ones, the root times the root goes away. Minus times minus is plus, so I should have plus 1 plus x squared. That's all underneath here, 1. Times this thing, square root 1 plus x squared minus x over square root of 1 plus x squared, like that. I should be able to combine some things together. 1 plus 1 is 2, so I'm going to put this here. Also, x squared plus x squared is 2x squared, so I get 2 plus 2x squared minus 2x root 1 plus x squared. All right, so that's what happens on the bottom when I collect like terms. Gosh, we multiply this through. Man, what do they go to? My goodness. You know, I guess I'll multiply that through. That's not very pretty, but I'll multiply it through. I'm going to go here and multiply it here, and here, and here. And then I'm just going to put this on top. Wow, this algebra on this one is messy, 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 messy. Okay, equals. All right, the top is going to be root 1 plus x squared minus x over. I was really hoping I wouldn't have to go through all this, but this times 2 is just 2 root 1 plus x squared. And then this times this is plus 2x squared root 1 plus x squared. And then this is the only good part. This times this, you get negative 2x. And then the root times the same root, the root goes away, so I'm left with 1 plus x squared. Has to be in parentheses because this negative 2x is going to multiply times it. So when I multiply that through, I'm going to have root 1 plus x squared minus x over 2 root 1 plus x squared plus 2x squared root 1 plus x squared minus, distribute here and here, 2x minus 2x cubed. Wow. My goodness. Oh yeah, I see it. Now, check this out. I'm going to factor just these two terms, GCF out of those two. If I pull out a GCF out of those two, I can pull out a 2 root 1 plus x squared. What I'd be left with is a 1 plus x, like that. Then over here, I'm going to pull out 1 plus x squared, x squared, right? Because I pulled out a 2 and a root, so I'm left with a 1 there. Pull out a 2 and a root, I'm left with just the x squared there. Out of this one, these two, I'm going to pull out a GCF. I'm going to pull out a negative 2x, and I'll be left with a 1 and then plus an x squared again. And notice that these both have a 1 plus x squared, so I can pull that out. And so on the top I have root 1 plus x squared minus x over the 1 plus x squared, which I pulled out. And I'm left with this piece and this piece, which is 2 root 1 plus x squared minus 2x. And I'm almost there. Notice these two have a 2. So I pull a 2 out. I'm just going to pop that 2 right there. That 2's not there. That 2's not there. And do you see it? Hope so. Those cancel. So I'm left with a 1 on top. And I've got 2 and then 1 plus x squared on the bottom. Wow. That's some algebra right there. I had a feeling when I saw that answer that they were going to want us to go further with it. All right, let's look at 21. Capital G of x equals square root of 1 minus x squared times arc cosine, right? They write it kind of different, arc cosine x. I don't like to use that notation. I like to use this notation. But they're the same notation. All right, I want the derivative here. So product rule right there, g prime x equals the derivative of the first one. Well, the derivative of root of something is 1 over 2 times the root of that something times, chain rule, derivative of what's in here, negative 2x. All right, that's the derivative of the first one, times second one, plus now the derivative of our cosine. So this again is going to be on page 183. It's going to be negative 1 over the square root, and they put the negative in the formula, they put the negative out front, but I just put the negative on top. So 1 minus x squared there. That's the derivative of our cosine x. Done. Times the first one, square root 1 minus x squared. These cancel. And then over here you get this 2 and this 2, so you have a negative 1 on top, so negative cosine inverse x over square root of 1 minus x squared plus, negative 1, so minus 1. I'm missing my x. Negative x, that x right there. Sorry, I canceled the 2's, but not the x's. All right, that's it for 21. 22, capital F of theta is arc sine of the root of sine. Wow. Capital F of theta is equal to arc sine of the root of sine of theta. Notice again I'm using this notation instead of writing arc cosine. And I have chain rule here. I have arc sine of a root of a sine. So 3 layers to this onion. I'm going to go, the derivative of this is going to be, well, what's derivative of arc sine of something? It's 1 over the square root of 1 minus that something squared. Or, yes, okay. So it's going to be, this is the something right here. Derivative of arc sine of something is 1 over the square root of 1 minus this something squared. And when I square that, I just get sine theta. Times, now, I've done the sine, arc sine. Derivative square root of something is 1 over 2 square roots of that something. So I've done the root. Now I take derivative of what's inside that, cosine theta. I just leave it like that, I guess. Okay. All right, 23. H of t. H of t equals cotangent inverse of t plus cotangent inverse of 1 over t. Now that 1 over t, I'm going to rewrite that as t to the negative 1. And let's try and take a derivative. So the formula for the derivative of arc cotangent of something is negative 1 over 1 plus that something squared. So again, going off the formulas, the derivative of this should be negative 1 over 1 plus that something squared. And that's all I need, okay, for that. Because if I did chain rule, right, I just did the outside, here it is, then I do derivative of t would be 1 here. So that's it. Plus, now, same thing, negative 1 over 1 plus whatever's in here squared. Now be careful with that. That's t to the negative 2. Because t to the negative 1 squared, you multiply the exponents, you get negative 2. But be careful, I have to do chain rule times the derivative of what's in here. Derivative of what's in there is negative 1t to the negative 2. So I bring the power down, subtract 1 from the power, I get that. All right. Let's see if I can't clean this up. This is negative 1 over 1 plus t squared. The negative and the negative here are going to become positive, so I'm just going to have plus, let me write it this way, 1 over 1 plus 1 over t squared, that's this right here, times this right here, and remember the negative's gone, is 1 over t squared. So what I'm going to do now is I'm going to distribute this t squared through both those terms on the bottom. I'm going to multiply it through. When I do t squared times 1, I get t squared. When I go t squared times 1 over t squared, I get 1. So I get negative 1 up front, 1 plus t squared, plus 1 over, and again, that's t squared plus 1, t squared plus 1. These have the same denominators, so we can add them together. Negative 1 plus 1, that's 0. This is 0. Huh. The derivative of that is 0. Always. It's always 0. The slope of the tangent line to that curve is always 0. Interesting. All right. Cosine inverse of sine inverse of t. Chain rule. So you start with the outer function, which is cosine inverse. The derivative of cosine inverse of something is -1 over the square root of 1 minus that something, okay, which is arcsine of t squared times, I've done that, what's the derivative of arcsine of t? 1 over square root 1 minus t squared. And that's it. We're just going to leave it like that. 25. Arctangent of cosine theta. Arctangent of cosine theta is number 25. Chain rule again. The derivative of arctangent of something is 1 over 1 plus that something, cosine theta, squared, but I'm just going to put the squared like that, times the derivative of cosine theta, which is negative sine theta. So I can just move that on top, and that should be good. X natural log arctan x. F of x equals x natural log of arctan of x. Product rule. Derivative is the derivative of the first one times the second one. So since the derivative of x is 1, this is just this. Plus the derivative of this. Now this is a chain rule. Derivative of natural log of something is 1 over the something. But then chain rule says, done derivative there, take derivative of what's inside, derivative of arctangent of x. It's 1 over 1 plus x squared. And then I have to finish it off by multiplying by x because that finishes off my product rule. And then you could just like clump this together on the bottom, put the x on top, and then that would be your whole answer. Okay, 27, this is my last one. X arcsine x plus root 1 minus x squared. X arcsine x plus square root 1 minus x squared. I just have a feeling the algebra on this one's going to get ugly, that they're going to want to clean it up. That's not so bad. All right, so look, take the derivative, two terms, so I can do each one of these separately, but this one is a product rule. So do a quick product rule here. Derivative of the first one is 1, so that's arcsine x, plus derivative of arcsine of x, which is 1 over square root of 1 minus x squared, times the first one, x. I'm done with this derivative. Plus, the derivative of the square root of something is 1 over 2 square roots of that something, times the derivative of what's in here, in there, which is negative 2x. So I have arcsine x plus 1 over the square root of 1 minus x squared. Then over here, when I cancel the 2's, sorry, this x is on top. X right there. And when I cancel the 2's, I get a negative x here on top. So plus negative x over square root of 1 minus x squared. And notice that these have the same denominator. I can put them together. X plus a negative x is x minus x. It's gone. This is 0. The answer is arcsine x. And I'm getting a phone call. Oh no, it's a meeting. Okay, I got to run, but it's perfect. I'm done with this section. So.